So when we first defined Newton's second law, I actually said that's a little kind of squirrely because really, hang on, I'm going to change this so we don't go the other direction. There we go. So that makes it a little easier to see. We started out saying that Newton really said that impulse is equal to a change in momentum. And we defined impulse as force over some incremental time. And we defined momentum as mass times velocity. So let's think about this for a second. And let's think about a basketball player that's getting ready to jump on the floor. The basketball player, we can use a variety of techniques, but one of the things we can figure out that our basketball player has a mass of 65 kilograms. And we can use our video analysis, we can use a variety of different tools, and we can determine the velocity of our basketball player after the jump. Okay, so we know what the velocity of that basketball player is. And we can use a stop camera or something, and we can find the time of the jump. And we can say that the time of the jump is 0.45 seconds. And this makes a lot of sense because we've been able to use our video analysis tool to be able to record some of that data. So we could actually do this. So what we want to do, we're going to use this data and we're first going to find the impulse. Well, that's easy enough. That's going to be our change in momentum, which is going to be our mass times our change in velocity. Our initial velocity, and we want to look at this, our final velocity is going to be that 1.8 meters per second. Our initial velocity is 0. We know that our person is 65 kilograms, so we've got our 65 kilograms times our 1.8 meters per second minus 0 meters per second. And our change in momentum actually is going to end up being 117 kilograms meters per second. So we can also think about the force on the floor. And if we think about this just before the jump, our force on the floor is going to be the weight of our basketball player. So we know what that is. That's just going to be mass times gravity. That's our 65 kilograms. And we've got 9.8 meters per second squared. And we have 637 newtons. So the force that the basketball player is applying on the floor and at equilibrium, our forces act in pairs. Forces act in pairs. So the force of the floor is going to be equal but opposite. And it's going to have a magnitude of 637 newtons. So if we want to know the total average force applied during the jump, and we know what the time of that jump is, we can do that because we know that my impulse is equal to my change in momentum. And we can look at the impulse as the force times my change in time, which is equal to my change in momentum. So my force is just going to be my change in momentum divided by my change in time. We got this change in momentum is 117 kilograms meters per second divided by my time, which is 0.45 seconds. And so I would end up with a number that looks like 260 newtons would be the average force that my basketball player is applying during the jump in order to get that change. So it gives us just a slight different way of looking at it. And if we want to, so this is the force applied. And if we want to know the net force that happens, that's going to be my force applied plus the force due to the floor. And now I've got 260 newtons plus my force on the floor, which is 637 newtons. So this is going to give me 897 newtons, which would be that average jump that we had happen. So we're going to look at this idea of force and impulse just a little bit different as well from another perspective, because we've played with this perspective a lot. So if I have a wall here and we take a ball and we have that ball hit the wall, we know what's going to happen because we've done this game. It's going to rebound off there. This angle and this angle are going to be the same. We know that that's going to be the same. So we can look at our idea of our, if we're going to say we have a 3 kilogram ball, and our ball has a velocity of 10 meters per second. We're going to give ourselves an angle of 60 degrees. And we're going to give our change in time for that collision to be 0.2 seconds. We can determine the force that's being applied here. So we're going to get my impulse is equal to my change in momentum. And that's going to be my velocity final minus my velocity initial. I got to times my mass here. And what we're going to have is we're going to factor out the mass, and we're going to look at these velocities here for a second. I can look at this, and we're going to have a velocity in the X and Y component. So in this case, this is Vx, which is going to be my velocity cosine of my angle. My Vx over here is minus the velocity. It's going to be minus the velocity cosine of the angle, because we can use this trigonometric identity that these two angles are equal. I have a Vy, which is going to be my velocity sine of the angle. This Vy is velocity sine of the angle. So if I look at my velocity final in the y direction minus my velocity initial in the y direction, my velocity final in the y direction is oh, I know what's going on. I did this funky. It's all right. My velocity final in the y direction is going to be V sine of the angle minus V sine of the angle is going to equal 0. My velocity in the x direction initial or final minus my velocity in the x direction initial is going to be V cosine theta minus a minus V cosine theta, and I'm going to get a positive 2V cosine theta. So I'm only going to end up worrying about the x component, and my force is going to be in the x direction, which will be the mass divided by the time. And I'm going to get a 3 divided by my 0.2 seconds times my 2 times my velocity, and my velocity was 10 meters per second. And this is in kilograms. And then I've got the cosine of 60 degrees. And that's going to end up being the force that's applied. And you may have a homework problem that looks like this, but be very careful as to what angle they provided you. Because my notes, I provided a different angle, which is why we're going to get a slightly different problem. But that would be, you'll plug that one into the calculator and you'll get your number. So we've got this idea of impulse, but let's think about what happens physically. So if I have a ball and I have another marble, so we're going to play marbles here. This one has an initial velocity of 0. This one has an initial velocity, we'll just give it 2 meters per second. And this is before the collision. This one has momentum. And if we say this mass is, I'm going to give this as a 0.1 kilogram. Momentum is going to be, we'll use this P, give it in our velocity, because this now has vector characteristics. I've got my 0.1 kilograms times my 2 meters per second. And I end up with my 0.2 kilograms meters per second. And then I have this idea of momentum. Now we've played marbles before, And we know if we have a perfect collision, what happens is the first ball ends up with a final velocity of 0. And if we said that this has the exact same mass, we know that the second ball moves off at a final velocity equal to that initial velocity if this is 0.1 kilograms. Because we've played marbles. We've actually seen this happen. We've actually seen these things collide. And this gives us our idea of conservation of momentum. Momentum is conserved. Because we've done this game. We've played this game a lot. We've played this game a lot. Now, if I have a perfect collision, and we call this an elastic collision, I also get something else. It's a special case. So elastic collisions are special cases. And in an elastic collision, we can conserve kinetic energy. And that's how we tell that we have an elastic collision. We can tell we have an elastic collision because we get conservation of kinetic energy. Now, let's go back and let's look at conservation for a second. So even though we haven't talked about it, but we know from chemistry that we have conservation. It's been a long day. We have conservation of mass. And this gives us our idea that if I start out with 5 oxygen molecules at the beginning of the reaction, and I react them with 5 CO2 molecules, so 5 carbon dioxide molecules. If I did that, I'm going to end up with 10 oxygens. Let's look at that for a second. If I have 5 O2s reacted with CO2 with 5 CO2s, and from chemistry, if you've had chemistry, that says I have 10 oxygen atoms plus 5 carbon atoms plus 10 oxygen atoms. And at the end of my reaction, I still better have 20 oxygen atoms plus 5 carbon atoms. All right, because that's my idea of conservation of mass. Now, we haven't really talked about that in physics so far, but the same thing applies. I'm going to have the same amount of mass that I start with. I should have the same amount of mass that I end up with, which is a little bit different than thinking about how we've thought about mass. We've also said that we have conservation of energy. So the total energy at the beginning has got to equal the total energy at the end. And even though we do get the idea that Newton's or the second law of thermodynamics, it says I can't get it all to go to work, but that's okay. But I still have the same amount of energy as when I start and when I finish. It's just whether or not I can make it go to work. Now we're saying we have conservation of momentum. And we know that because we've played with collisions before. And we've been able to see that over and over again. And this type of momentum is referred to as linear momentum. So I'm going to have linear momentum and I get conservation of momentum. So let's look at the types of collisions that we might have. We might have a collision just like our balls here. So I have this ball that goes over and hits this one. The first one stays and the second one goes off. So this is the before. And this is the after. Okay. Now, if we play with this, if mass 1 is equal to mass 2, this velocity 1 will end up as velocity 2 will equal velocity 1 if the masses are equal. Now, we've done this before, right? We've played this game before, where if mass 1 is twice the mass of 2, then what happens afterwards is I'm going to have M1V1 is going to equal to M2V2 no, I'm going to have my M2 there, and then I'm going to plug in my 2M2V1 is equal to M2V2. Those will cancel, and V2 or V1 or twice V1 will equal V2. Or it's going to go off as half of the velocity. So we can actually predict how fast something's going to happen when we have those velocities change. And again, this is when we deal with an elastic collision. Then we have the type of collision. So I have a block here, and I have a little bullet here. So this is the before, and this is the after. And in the after, the little bullet is now part of the block. This is referred to as a totally inelastic collision. And then real collisions are somewhere in between. This is a real collision, but I also have cases where they're not completely elastic, but they're not totally inelastic. You can call those glancing. You can call those a variety of different things. But it turns out we can model a lot of systems as elastic collisions. A hockey stick on the hockey puck, that can be modeled very easily as an elastic collision. Even a basketball bouncing up and down, even though we know we get a little bit of deformation, we get a few other things, it still is going to work really, really well. Interactions with ball bearings, marbles, or playing pool or billiards, all of those things can be modeled after elastic collisions, and they're modeled quite well. Totally inelastic collisions are also really easy to get there, but the big thing is that the momentum before has to equal the momentum after. The momentum before has to equal the momentum after. And that's going to allow us to do a variety of different things. We can actually work through a lot of different type problems that we can play with. So in the interest of time, in the interest of showing a few things, I'm going to show you the basketball problem. And we're going to actually talk through this. Now, you guys do have this basketball problem worked as an example problem. And a lot of you have seen this trick. You take a tennis ball and a basketball, and you're going to drop it from a height. And when the basketball starts to rebound, it's going to impact our tennis ball. And then our tennis ball is going to shoot up. So we are going to do, and usually when we're dealing with momentum problems, we can also play with conservation of energy problems. But what we're trying to do is we're trying to find the height of the tennis ball after the collision. Well, the first thing we're going to need to know is we're going to need to know the velocity that the basketball hits the ground with. And we can use our conservation of energy. My potential energy is going to equal my kinetic energy, and we can actually use these numbers, use our real numbers here, and I get 4.7 meters per second. And now I'm going to write my conservation of momentum equation. The mass of my basketball times the velocity of my basketball plus the mass of the tennis ball and the velocity of the tennis ball, and this is all before, has to equal the things after. And since the mass of the basketball doesn't change and the mass of the tennis ball doesn't change, we can leave those in like that. But one of the things that we do know that initially, when the basketball hits the ground and starts to rebound, at that exact instant, the basketball's velocity is positive, but the magnitude is the same as that of the tennis ball, and we're going to go reverse. So now I can substitute in for my tennis ball, and then I have my idea of my momentum before and my momentum after, but I've gotten rid of one of these variables. Okay, well, I have the mass of the basketball, so I still have two unknowns here. And so I have to think about it a little bit. Now, we did say that if I have an elastic collision, the kinetic energy before has got to equal the kinetic energy after. And we're going to do some Gorey algebra. Okay, we're going to do some Gorey algebra here to get some rearrangement so that we can ultimately get an equation that looks like this. Because we'll do some factoring and we'll do that nice rearrangement. And we get this really cool result for elastic collisions. A totally cool result that I get the velocity, initials of velocity find. So what we're going to do is we're going to put that into our basketball situation. And what that says is that the velocity of the tennis ball before plus the velocity of the tennis ball after is equal to the velocity of the basketball before plus the velocity of the basketball after. Now I'm going to put my befores on one side and my afters on the other, and we're going to solve, and we're going to get this lovely equation, which we're going to ultimately plug into our first equation. And that goes back to this equation right here. I'm Gonna do some more Gorey algebra and plug in some numbers. Get to Gorey algebra and plug in some numbers. And you're ultimately going to show that the bat or the tennis ball is going to jump up by 8 meters for that particular item. So you can play with these equations to get you a long way around. And that's got, like I said, that I do have that one is out there for a variety that I step by step through it, work through it, and get those things taken care of. So we're going to do a couple momentum problems here. Let's start with I have an object that's going to come in with an initial velocity of 3 meters per second. It's going to have a mass of 1 kilogram. It's going to hit an object that has an initial velocity equal to 0. It has a mass of 1.5 kilograms. We're going to, this time we're going to assume a perfectly elastic collision. And we want to know the final velocity of the second ball. Now, this one isn't going to be too difficult, but I want to kind of walk through it because we're going to do one that's a little more difficult. But I want to just walk through the idea of how to do this. So we want the momentum before. Has to equal the momentum after. All right, momentum before has to equal the momentum after. So let's do that. So I'm going to have the mass of ball 1, the initial velocity of ball 1. And this is where using these little subscripts is going to come in very, very handy. It'll keep track of your which ones you're working with. So I get mass 2 is equal to my velocity initial 2 is equal to mass 1 velocity after plus mass 2 velocity 2 after. If we have a perfectly elastic collision, it's mass 1 and 1, and this is my after. If I have a perfectly elastic collision, this is 0 because my velocity after is supposed to be 0. Doesn't always happen that way. I might get this one to dribble off, but I can account for that in this equation. But we're assuming a perfectly elastic collision. Our initial velocity of our second one was equal to 0. So now I know my velocity or my momentum of my first one has got to equal the momentum of the second one. And now, since that's what I'm looking for, I'm going to get M1 divided by M2 velocity 1 before. It's going to give me 1 kilogram divided by 1.5 kilograms times my 3 meters per second will give me my velocity after. And I have left all my calculators in another room. So we're just going to leave that at this particular one. So let's do something similar, except now we're going to do what's called an inelastic collision. So I have a bullet And my bullet is going to, well, we're gonna, let's change that. This is, we're gonna assume a inelastic collision here. And we're gonna use the idea. So I have a train. And I have a cow catcher on my train. And my train is going to come down the road at 27 meters per second. It's going to have a mass of 10,000 kilograms. And we're going to have a lovely little Dr. Seussian beetle car here that has a mass of 2,000 kilograms and is stuck on the track, and its initial velocity is equal to 0. We want to know, we're going to be nice to the little car. So this is the before situation. The after situation is going to look a little bit like this. We know the after situation is not really like that, but we're going to be nice to the little car. We're going to let it come up together. And so the mass after is equal to the mass of the train plus the mass of the car. And the velocity after is a combined value because these two things are now one object. So I can write out my conservation of momentum equation, mass of the train times velocity of the train plus mass of the car, velocity of the car, has got to equal the mass after times the velocity after. Well, my car started out at 0, 0. So now I get the mass of the train divided by the mass of the train plus the mass of the car times my initial velocity is going to equal my velocity after. So this is going to be 10,000 divided by 12,000 times 27 meters per second will end up with my velocity after. And if we think of about a big train, we know that the bigger the train, the little car doesn't stand a chance. You're going to lose that battle. You're going to lose that battle all the time. Now, a trivia item, just for trivia purposes, by how I drew my train, I can tell you the fuel source on that train. Because the smokestack on your train, if you were thinking about trains from, because I'm a train buff, I like trains, I think trains are cool. If you look at your golden spike picture, you look at your golden spike picture, the trains from the west look like this, have your little cow catchers. And the trains from the east look like this. And it might also have a cow catcher. But this stack had a spark arrestor. Because it used wood as its fuel source. This used coal, didn't need a spark arrestor. So you wouldn't start wildfires. So if you look at your golden spike, this one came from the west, that one came from the east. These were running off of coal. Those with the spark arresters are running off of wood. Just a little trivia on on looking at trains. All right, so there's some interesting things that we can play with on these problems, one of which is called the ballistic pendulum. Now, my ballistic pendulum would start out with a little bullet, ends up with a block of wood, and this is attached to a pendulum here. And the after situation would have the pendulum would rotate up to a new height. So we have a new height here, and now the little bullet is inside of this. And it's a way to measure the initial velocity, because I'm going to use both conservation of energy and conservation of momentum. So over here, I have the mass of the bullet plus the mass of the block. And this is the velocity of the bullet, velocity of the block. On this side, that's going to equal 0. Now over here, I have after. I have the mass of the bullet plus the mass of the block. Times the velocity after. But I don't know that velocity after, and I'm wanting to find this initial velocity. Well, I can use conservation of energy to get that. So I've got my mass of the bullet plus the mass of the block, gravity times the height, and I've measured height. That's got to equal 1/2 mass of the bullet plus the mass of the block, v squared. Those things go away. I get 2gh is the square root. I now have my velocity, and now I can plug that back in to this one. So I get mass of the bullet, velocity of the bullet is equal to the combined mass square root of 2gh, velocity of the bullet, then becomes and I only have to make a simple measurement of the height of my block. So we can use the ideas of conservation of energy and the ideas of conservation of momentum in order to give us a couple of calculations that are out there. So we could play with that. Then we've done the basketball problem. And that kind of gets us in there. So on Monday, when we get back together, I will we'll do a couple more momentum problems, see where we are there. We will talk about center of mass. Want to get center of mass, maybe do some Newton gravitational problems. So we've got those covered. And that way we can start right into rotational motion after that. So tomorrow, of course, we've got a test and we can go from there. So I'm going to turn it over for questions here.